So this is Lab 5, Faraday's Law. In this lab, we're collecting observational data of a magnet falling through a roll of aluminum foil, and then we're modeling that interaction in GlowScript to compare the observed data to the computational predictions. This is a little summary of my lab. I found the experimental time of the magnet in the tube to be 1.02 seconds, and the theoretical time from GlowScript to be 1.305 seconds. Some of the fundamental physics principles I used in this lab were Faraday's law, which says any change in magnetic environment of a coil of wire will cause a voltage to be induced in the coil, and that says that the induced EMF in a coil is equal to the negative rate of change of magnetic flux times the number of turns in the coil. I also used the magnetic field of a dipole formula, which is this here, and Biot-Savart law, which is this here. So for the experiment, I first identified the north pole of the magnet. Then I held the roll of aluminum foil vertically and dropped the magnet through the opening. And I took a recording using my phone to find the time that the magnet was in the tube. And I did this 5 times to find the average to be 1.305 seconds. I then started coding, and I created my aluminum foil tube to the dimensions that I found in real life, where the length was this, the width was this, and the inner radius of the aluminum foil was this. And the code created a aluminum foil tube for me. Then I created the bar magnet with its initial conditions, and for the bar magnet I used the mu that I got from lab 3, which was 2.01, and I found the mass of my bar magnet. I also created 2 functions, one being the magnetic field function from the formula earlier, and the other being the magnetic flux function, using also one of the formulas from earlier. And using this function, I'll be able to find this blue ring and this red ring, as shown in the next slide. So here I calculated the positions of the rings throughout the whole tube, and then calculate the gravitational force on the magnet here. And then I needed to calculate the magnetic force on the magnet. So I did that by running a loop for the rings in the tube and used the function from earlier for d flux dt, and was able to find rings that were blue and red like this. So I calculated the current in the ring using Faraday's law, and then computed the typical B field at each of the rings using the dipole function from earlier. Then I found the magnetic force on the magnet doing this, and found the net force by just adding the gravitational force and the magnetic force. And I needed to update the position and velocity of the magnet by applying Newton's second law, F equals ma, using this code here. And overall, after doing all of this, I was able to plot the velocity versus time graph of the magnet as it dropped through the roll of aluminum foil. So for my graph, I was able to get a graph that looked like this, and my time to be 1.305 seconds, which we see is pretty similar to my experimental value. And I also noticed that red would be counterclockwise for our current when viewed from above, because the induced magnetic field points up, and vice versa for blue. I also saw that the dynamics of the system don't change when I flip the magnet around. Overall, I saw that the times between my experimental and theoretical values were pretty similar, and there was only a 0.285 second difference. And it could have been, the computational system could have been made a little bit more accurate if I used a more accurate mu value. And also I was able to see that the shape of the graph of the velocity versus time graph tells us that the gravitational force and magnetic force acting on the magnet eventually reach equilibrium, as shown by the constant velocity. And then we also had the questions of what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the magnet change. So we'd see that the induced current would increase with reduced resistivity, and thus the magnetic force increases and the magnet falls slower. And if there were holes or slots cut into the tube, then we knew that with less complete rings, the resistivity would increase and therefore the induced current would decrease. So opposite to what happened in this first question, the magnetic force would decrease and the magnet would fall quicker. And overall, we were able to find these two values, and our glow strip code connected the relevant physics principles to the model used to represent the real system. And it basically just showed how much time it would theoretically take for the roll of aluminum foil for the magnet to fall through the roll of aluminum foil, and we were able to compare that to our experimental time.